Right. Good evening, everyone. Welcome to this session on communication systems, important concepts. Already I have taken one session on Saturday. There I have given you how to prepare for GATE examination in terms of communication systems subject. So it's like a preparation strategy. What is the expected weightage from each topic and how many questions you can expect, what are the areas you need to focus, how to divide your entire syllabus into small chapters and study. So hope that session is useful to you. Today I am taking one more session covering important concepts. So when it comes to covering concepts, especially in communication systems, you know it's a pretty big subject. So for that 1 hour duration which I want to take, I want to make some concepts very clear for you. Most of the students, you know, they feel a little bit difficult, or I should say frankly very difficult, when they go into the area of calculation of probability of errors, especially in digital communication systems. So today I will touch that particular concept. I will actually derive what is that optimized value of voltage that you have to take so that your probability of errors will get minimized. So every time whenever these questions are framed, they will use algorithms like MAP and ML algorithms. What are those algorithms? How you have to identify them? Only those points I will touch. I will give that derivation. Practically we will do it now. And one more thing, if the time permits, I will also concentrate one question on constellation plot. So generally these are the areas where a little bit of more focus is required by you, because all the other areas straight away they are mostly formula based, 1 mark questions, but 2 marks questions are coming especially from these areas where you need to focus more on this particular region. So let us not waste any more time. Straight away let us go into this topic. Okay, right. So the first topic I am covering is optimal reception of signal, optimal receiver in digital communications. So what do you mean by this optimal receiver? First of all, because 2 words are there. We are using optimal receiver. It's a receiver which is optimized and particularly used for digital communication. So it can be used for baseband or band pass, but general discussion will be for band pass. Okay, right. Let us see that. Now, just understand the concepts. Basically, whatever the signal that you will get at the input of the receiver. So this is what you will be getting at the input of the receiver. Now, whatever you get is R of t, signal coming at the input of the receiver. This is a combination of your signal component and noise component. Clear? That is the first point you need to keep in mind. Signal component as well as noise component combined together is your received signal. Now, for easier understanding, your bit 1, whatever the modulation scheme might be, is represented as S1 of t, and the bit 0 is represented by S2 of t. It's a standard notation followed in many textbooks. So this is the representation of my modulated signal coming at the input of the receiver, independent of the type of modulation scheme. It can be any scheme, okay? ASK, PSK, FSK, whatever it might be. Now, what about noise? N of t, whatever is considered, is a random process which is taking the form of additive white Gaussian noise. That means what? This noise will get added with your modulated signal. White means what? It affects all the frequencies equally. Gaussian noise means the PDF of this noise is taking the form of a Gaussian random variable. That is the meaning in this statement. Now, whenever you take this, the mean value or expectation is taken as 0. So the mean value of additive white Gaussian noise is 0, and it has a variance sigma square. So this is a general exemption that we take, because the channel that we are considering here is completely a free space channel. Free space channels are modeled using this part. I hope my points are clear. Now, once you get your signal at the input of the receiver, it will be processed through various blocks. Like if you take a synchronous detector, what will happen? Your signal will get multiplied by carrier and then goes to a low pass filter, and then it will develop an output voltage. Okay, so let it be any type of receiver. Receiver model is up to you. Once it gets processed, I am not taking all the blocks. I am just taking the processed component. So what I mean here is, once your receiver structure is completed, means there is some block here, it can be anything, synchronous detector, non-coherent detector, anything. You will get a processed signal here. Processed signal I am writing as R naught of t. So again, this is a combination of your processed signal component and processed noise component. This is very, very important point. So whatever the signal that comes at the input of the receiver, it goes to various blocks and then comes at this stage. Now this S naught of t, I am writing S naught 1 of t as some V1, means when signal for bit 1 came at the input of the receiver, after it gets processed, its voltage is V1, and once you have bit 0 coming at the input of the receiver, after it gets processed, I am writing as V2. So this is the signal component part. Is it clear? Now your N naught of t is also a noise random process, because at the input of the system it is random process. Here also it should be a random process. Now the value of mean at this stage is definitely 0, because if you take any system, input mean 0 means what? Output mean is input mean multiplied by transfer function value at f equal to 0. So if you take input mean of any process 0, obviously the output mean must be 0. There is no value. And the variance or power I am writing as sigma naught square. Did you get my point or not? So these are all the things that are coming at this stage. Now, once you get these things, what we do is we sample this value. Sample means here taking. So these values are considered at some t equal to tb seconds, bit duration. That means you are considering the signal component as well as noise component taken at t equal to tb. Now, here comes the very, very important block. We give this as an input to a threshold detector. So generally threshold detector symbol is represented in this fashion also. Some textbooks follow this notation also. So even in examination papers, sometimes you might be given like this also. So this is what we call it as a threshold detector. Very, very, very important block. Another name for this threshold detector is decision making device. Try to understand these points. Those who are having little confusion or don't know this concept also, you can easily pick up from here. This is the most important block. Why? Because the output of my receiver has to be binary data. That means you have to develop the bit sequence BK here. Is it clear? How will we develop the bit sequence? You have this R naught of t, right? Coming at this stage, sampled at t equal to tb. So what we do here is, we set a threshold voltage VTH here. So what we do is, we write an algorithm. If this value of R naught of t at t equal to tb happens to be greater than or equal to VTH, then you decode it as bit 1. If this value of R naught of t at t equal to tb is less than VTH, then you decode it as a bit 0. This is a simple algorithm that will come at the last stage of any digital receiver. Got my point? Now, definitely it will go as per this algorithm, develops a bit sequence. Now, there is no chance every time your bit might be correct. So what happens? There might be a chance that 1 may become 0 or 0 may become 1. So this is where we develop probability of error. Got my point? Try to understand in a simple way. I did not take all the processing blocks here. There might be any block depending on your receiver. Once that signal and noise is processed, then it will go through this stage. So this is the last stage of any of your digital communication receiver. Got my point? Now, what is our target? Whatever the probability of error you get here has to be minimized. So any communication receiver, you should not leave as it is. You have to see that the probability of error you are getting is minimized. Now, if you want to minimize that probability of error, which is the logic you have to follow, you have to carefully select this threshold voltage. Because on this VTH only, this is coming. That means this VTH value which you are using here has to be optimized. This is what we call it as optimum value of threshold voltage. So when you optimize your threshold voltage, then automatically your probability of error will get minimum. That is a concept. I am repeating the statement. When you optimize your threshold voltage, then the probability of error which you get will automatically get minimized. Now, who will optimize that? Who will tell you what is the optimized value of threshold voltage? That is given by MAP algorithm or MAP rule. So this is how your questions will be framed in your exam. So whenever you use this MAP rule based algorithm, automatically your threshold voltage is set to be optimized and your probability of error will automatically get minimized. So in exam, either the question will be to calculate minimum probability of error. That means automatically this rule is applied, optimum value is determined. Or he may ask you what is optimized value of the threshold voltage. Apply this rule, get this value, stop there. So that is how you have to use this rule of MAP, maximize a posteriori algorithm. Very, very important and a beautiful algorithm. Okay, so this is a concept that you need to understand. I hope all my points are clear. Okay, now let us see, using this MAP rule, what would be the optimized value of my threshold voltage. Is it clear? Now understand the signal component part and the noise component part clearly. So once you have your signal and noise at the input, what will be the signal and noise after getting processed? That is what you need to understand carefully here. Okay, now see this. So your input noise is additive white Gaussian noise whose mean value is 0 and whose variance is sigma square. That is clear. Input signals either S1 or S2 if it is bit 1 or bit 0. Clear? Now what we are saying, your R0 of t processed component has either S01 of t at t equal to Tb. This only we are writing as V1, correct or not, plus the noise component N0 calculated at t equal to Tb. Did you get my point or not? Processed value. Similarly, the received voltage after getting processed, if it is bit 0, we are writing it as V2 plus N0 of t at t equal to Tb. Done. Clear? Now, if you take the expectation of this signal, what is expectation of R0 of t? This should be equal to expectation of V1 plus expectation of N0 of Tb. Correct or not? Now, you know expectation of a constant is a constant and expectation of this component is 0 or not? Because input noise mean is 0, wherever you calculate mean at any stage it will be 0 only. That means the expectation of the processed signal coming at the input of your decision making device is V1. Got it? Similarly, what is the expectation of R0 of t at t equal to Tb? This will be again the same expectation of V2 plus expectation of N0 of t at t equal to Tb. Finish. Now you know mean of a constant is constant. So therefore expectation of R0 of t will become V2, which is a constant. Second component automatically becomes 0. Now, what are these? These are the mean values of your processed signal coming at the input of your threshold detector or your decision making device. Did you get my point or not? That means if you take the density function at this stage, let me keep it like this. Again, you should not get confused. Okay, now if you take this particular mean value of the processed signal coming at the input of your threshold detector, its mean value is V1. Which density function you are expecting? It should be Gaussian only, because this is a deterministic, this is random. Which is a Gaussian, which is a random variable you are taking here? Gaussian. Randomness added with deterministic is random only. So the net should be random only or not? That means the net value of this function R0 of t for S1 transmitted should be a Gaussian random variable whose mean value is V1. Got my point? That means the density function of the received signal when S1 is transmitted, conditional density function. Whatever the received signal you are getting at this stage, when S1 is transmitted, is equal to, it is taking the form of Gaussian function, 1 by root over 2 pi. Instead of sigma, I am writing sigma naught, because processed mean square value or variance into e power minus of, it can be any value of your received voltage. We don't know. It can be anywhere from minus infinite to plus infinite. Minus, what is the value of mean? V1 whole square divided by 2 sigma naught square. Finish. Where your R value can lie anywhere between minus infinite to plus infinite. Got my point? Similarly, when you have transmitted S2, it comes at the input of the receiver, gets processed to all the blocks. The mean value of the received signal, which is coming at the input of your threshold detector, is V2. Its density function is also Gaussian, because this is Gaussian. So what is the density function of the received signal when S2 is transmitted? So this will be 1 by square root of 2 pi sigma naught square into e power minus of R minus V2 whole square by 2 sigma naught square. Finish. And this R can take any value from minus infinite to plus infinite. Do you get my point or not? So this is the crux of this entire story. This you have to understand clearly. Is it clear? Now, if you just plot it, that means, suppose if you take this density function and plot it. So let me take my x-axis. So here my x-axis is received signal after getting processed, R0 of t. Okay, so what is my density function? My density function is having two components. One is a Gaussian random variable whose value of mean is V1. Another one is also a Gaussian random variable whose value of mean is V2. So if you take it and draw, this is how it looks like. So let me take a Gaussian function. Okay, so let me consider it is having a value of mean which is equal to V2. Just for example, I am taking. Now, I will take another color. You are having one more Gaussian function whose value of mean happens to be V1. Okay. Done. Try to keep it as simple as possible. Now, the value of this mean is V1. Clear? Now, what is this representing? This represents the density function of your received signal when S1 is transmitted. If you want, you can write R0 also. I am just keeping as R. Previous page I have written as R. So I am keeping as it is, okay? And this represents the density function of the received signal when S2 is transmitted. Conditional density functions. Clear? Now, you can observe here, the height of both these functions are same. That means I have assumed that the probability of S1 and probability of S2 are same. This is just an assumption to draw this graph. What will happen if probabilities are not same? One graph will have more height, another graph will have less height. That's all. That is the only point. Okay? Now, what this MAP algorithm tells is very simple statement. The minimum probability of error will occur at the point of intersection of these density function curves. That is what it says. One line statement, simple. So where are these curves interacting? This is interacting at this point. Correct or not? So whenever you have these conditional density functions curves for both S1 and S2, the point of intersection of these density function curves is your optimum value of threshold voltage. That's all. That means if you set your threshold detector VTH as VOPT, which is the point of intersection of these two curves, then automatically the probability of error that you get here will get minimized. That is the meaning. So that is the reason why we are interested in calculating VOPT. Now remember guys, whatever the so much theory part that I am covering, it will be same even if you take noise as different density functions. It need not be only Gaussian. The logic is same even when your noise is represented by uniform random variable or a double-sided exponential, or for that matter Rayleigh random variable. It can be anything, but most of the times our noise is continuous only. We don't take the discrete case, so our random variables will be also continuous. That is the only point. I hope you are getting my point. Clear? Now, what this MAP algorithm tells, what is the statement it tells is, observe this point carefully. For all the values of the received signal, means what? R. Okay? So this is actually I am writing as R0. Don't get confused. If you have doubt, just remove it for time being. Okay? Let us assume R. For all the values of the received signal, if the chances of finding S1 is more than S2. So instead of writing just to make it easier, instead of writing F, I will write P. For all the values of the received signal, because P or F both are same. F is representing your density function which deals with the probabilities. So instead of writing F, I am writing P. There is no change, no need to worry. For all the values of the received signal, means what? It can be anything on this x-axis, from minus infinite to plus infinite. What I am saying, if the probability of finding S1 happens to be greater than S2, then you decode the signal as S1. That's all. That means what is my meaning? What it says, common sense, that's all. See here. Your received voltage can be anywhere from minus infinite to plus infinite. That is clear. Correct? Now, let us assume your received voltage is coming somewhere here. You have a understanding or some sort of assumption. It is coming somewhere in this region. Your white curve is also here. I am saying it is there, but most of the times it may come in this yellow region. That means what is the meaning? This curve is belonging to your S1 or not? That means you can decode it as S1. If it is reverse, that means what? Whatever the value of the received voltage you are getting, it may come somewhere in this white color region. Here also yellow region is there. That means chances of 0 becoming 1 is also there. But chances are less. Then what you are saying, you decode it as S2. That means what you write here, if it is less, decode as S2. Finish. So this statement is your MAP. Finish. This is whenever you write greater, less like these symbols, this subject comes under statistics. It is also called as hypothesis. It is a simple concept based on your assumption, taking into consideration probability. I hope you got my point. Okay. Now, what I will do here is, we will apply Bayes theorem concept. I hope this is useful to you. Instead of covering only questions, this concept is very, very important and a definite 2 marks question. And most of the students have so many doubts in this area. So just I want to take only this particular concept and explain it to you very clearly. It's not completely given in any textbook. It is given. You refer to any digital communication books, it will be there. But it may not be so much sophisticated that you can understand very easily. So try to understand the points which I am telling here. See the concepts which I am taking. Then you will get an idea. Now, if you take Bayes theorem, what is Bayes theorem telling you? Tell me. Simple. If you take conditional probabilities, probability of A given B, you can express this as probability of B given A into probability of A divided by probability of B. That's all. This is the meaning of Bayes theorem. Conditional events whenever you are having, you can apply this logic. Now, I am applying the same logic on this. So what you can do here is, I can write this as probability of S1 given R. I can write R given S1. You have to multiply it with P of S1 and then divide it with P of R. Clear? If it is greater, we are decoding as S1. If it is less, we are decoding as S2. Finish. Into, you will have P of R given S2 into P of S2 whole divided by P of R. So what will happen? These two terms will get cancelled. So what we are getting now? P of S1 into probability of received signal when S1 is transmitted. If it is greater, decoded as S1. If it is less, decoded as S2. Into P of S2, probability of your received signal when S2 is transmitted. Finish. That's all. So this is how you are applying that MAB algorithm and Bayes theorem concept, getting this expression. Now what we are saying, your probability of error will be minimized when you take your VTH as VOPT. So what is that VOPT? It is a point of intersection of both the density function curves. So what you can write here now, P of S1 into, this is nothing but your density function of S1, density function of the received signal when S1 is transmitted, means 1 by root 2 pi sigma naught square e power minus of R minus mean is V1 whole square by 2 sigma naught square. Finish. If it is greater, decode as S1. If it is less, decode as S2. Got it? Into P of S2 multiplied by 1 by root 2 pi sigma naught square into e power minus of r minus v2 whole square divided by 2 sigma naught square. Finish. Got my point or not? Now, what we are saying here, probability of error will be minimum when VTH becomes VOPT at point of intersection of both the density function curves. That is a simple statement. Clear? That means what you can do, you can simply replace R with this VOPT. That is what we want, optimum value of the threshold voltage. When you can take, instead of greater less, you equate. That means what we can write here is P of S1 into this 1 by root 2 pi sigma naught square will automatically get cancelled on both sides. So I am removing here only, into e power minus of VOPT minus V1 whole square by 2 sigma naught square equal to, coming at the point of intersection of both the density function curves, P of S2 into e power minus of VOPT minus V2 whole square by 2 sigma naught square. Done. Finish. That's all. Now your target is only to calculate that VOPT. So this much of calculation is there. So MAP is a very, very powerful algorithm. It is applicable in all statistics. Don't think only in our communication. I will tell you one very simple example. Suppose you take any electoral system. That means, say there is some election going on in your particular city. Okay, so they will not take the entire city at a chance, right? They will divide them into wards, municipalities, like that. Suppose, let us assume you are there in your municipality, or you are, say, in your ward. Some 100 houses are there in your ward. Okay, so how these politicians will make their assumption whether they will win or lose, that is also probability only. 100% no one can tell. Until and unless, if no other competitor is there, only one person is there in the election, he will only win, unanimous. If two or more than two competitors are there, then obviously everything is related with the probability only. The statistics concepts very well work there only. That is the reason they are highly paid. What they will do there is, in 100 houses are there, that means in that ward. When this election campaigning keeps on going on, at least for 1 week or 2 weeks it will be there. By the end of that election campaigning, they will take the grip of these 100 houses. Means what? Grip in the sense, the feeling, which person is getting attracted to which person. That means some 2 or 3 fellows are there who are in that particular election. So the members staying in these 100 houses, let us say some 500 voters are there, 5 voters per each house, to whom they will vote. Generally, when 5 persons are there, they will not vote for different people. In a family, very rarely each person will go and vote for different person. Generally, they will come to a conclusion. They will take that sample voters. So out of that 100 houses, they will select some 10 and see out of these 10 houses who are giving vote to which person. Like that, they will come to a conclusion and they will tell that this person may have a chance to win. They will never tell 100% probability there. So that is the reason whenever elections are going on, exit polls they will tell. What is that exit polls? This concept only. This MAP is used there also. They will do the same thing. If that sample voters are more towards one person, they will tell that person has more chance to win. But that does not mean he will win complete votes. That is not correct. Maybe 60 to 70% chance. In election like campaigning, 50, 55 is also a very big figure. So that is how these algorithms are used. In our communications, we will use it like that. We are also saying the same thing. If your value comes mostly in that yellow region, S1. If it comes more in that white region, S2. That is the same thing we are also doing. That R value which you are getting is a sample there. So based on that, we are making an assumption. But luckily, we don't have more symbols. Only two symbols, either bit 1 or bit 0. Got it? Now, simplify here. So what you can do here? You can write this as e power minus v square OPT minus v1 square. I am just squaring it and multiplying with minus. So you will get v square OPT plus v1 square when you multiply with minus, and then you will get plus 2v1 VOPT. Minus of minus will become plus. This term will come in denominator. So when it goes to numerator, that minus will become plus. So you simply write that. That means it is plus v square VOPT plus v2 square minus 2v2 VOPT. So this entire value is divided by 2 sigma naught square. Done? Okay, and this entire value on right side, you can take P of S2 divided by P of S1. I hope all these points are clear. Okay, let me change the color. Now, what are the terms you can get cancelled? This V square OPT, these things will get cancelled. And if you take a natural logarithm on both sides, so natural logarithm of e to the base e will become 1. So you will have on the other side ln of P of S2 by P of S1. So what are the components you are having here? V2 square minus V1 square plus, if you take VOPT as common, you are having 2 into V1 minus 2 into V2 is equal to 2 into sigma naught square natural logarithm of P of S2 divided by P of S1. Ln is natural logarithm, be careful. Okay. Now, what is my requirement to find VOPT? So I am taking a VOPT into 2V1 minus 2V2 is equal to V1 square minus V2 square plus 2 sigma naught square into natural logarithm of P of S2 by P of S1. Finish. So you simply divide it with 2 into V1 minus V2. You can write this as V1 minus V2 into V1 plus V2. So what will happen here? The value of VOPT, optimized value of threshold voltage, will be V1 plus V2. V1 minus V2 will get cancelled, divided by 2, plus 1, 2 and numerator 2 will get cancelled, sigma naught square natural logarithm of P of S2 by P of S1 whole divided by V1 minus V2. That's all. So this is how you are getting the formula for optimized value of the threshold voltage. So if you select this optimized value of the threshold voltage, I am not saying that there will not be any error at all. Please be very clear. There will be error, but the probability of error that you are getting at the output of your receiver will get minimized. That is the meaning in this story. So the logic will be same when the noise changes its format. Here we have taken the standard case of noise as Gaussian random variable. Your noise need not be every time Gaussian. Examiner can give any type of random variable. The procedure for doing will be same. So where is the optimum value of the threshold voltage you are getting? At the point of intersection of both the density function curves. That is the first observation. Then based on your random variable, you are calculating that optimized value of the threshold voltage. So where you can use this formula? You can use this formula only when noise takes the form of Gaussian random variable. Then only you can use it. Otherwise, we cannot use it. So most of the times the questions coming in your exam, sometimes direct formula based. Easily you can answer. So here, suppose let us assume I am using a polar coding scheme. Polar coding means what? You will use bit 1 as a positive voltage, bit 0 as negative voltage. So automatically when they get processed through different blocks, the value of V1 and V2 will be exactly equal but opposite in sign. That means the sum of these two, first part of your optimized value of threshold voltage automatically becomes 0. Now, if you take a P of S1 happens to be equal to P of S2, that means the diagram which I have shown, correct or not? Then log 1 will automatically become 0, means this entire part is 0. That means the value of optimum threshold voltage in this case becomes volts. Sorry, I have a little problem with the throat. Please don't mind. Clear? Now, if you apply again the same polar coding, that means again V1, V2 are exactly same values but opposite in sign, so they will get cancelled. First term will become 0. Now, if you take value of P of S1 to be greater than P of S2, that means your density function curve when S1 received is more height and the density function curve when S2 received is less height. Then what will happen? This P of S2 by P of S1 will become less than 1. Log of a value less than 1 is negative or not? There is no chance power is negative, it is positive. V1, V2, V2 is negative of V1, so this value is definitely positive. So don't worry about this component, this is every time positive. This is becoming negative. So 0 plus negative value will be negative. That means your value of VOPT will be strictly less than 0. That means strictly negative value. How much negative value? When you substitute the values, you will get it. Similarly, again if you take the same polar coding scheme, where I have selected a P of S1 as less than P of S2. Probability of occurrence of S1 is less than S2. That means what? This ratio will become now positive. Then already this part is positive, 0 added with the positive value will be positive. That means your optimized value of threshold voltage is definitely positive or strictly positive. So depending on the coding scheme, sometimes instead of polar coding, he may give you on-off coding also, or any other coding scheme he may define. So that will tell you the first part. This part and this part is always positive. So don't need to worry about the sigma naught square, always positive. V1 minus V2, depending on the coding scheme, you will get the value. And you decide this factor. So only factor which plays the important role here is this natural logarithm of P of S2 by P of S1. That is very, very important for us. Hope you got this point. This is how you have to understand the concept. So if you are knowing that the noise given by the examiner is Gaussian, if you want to calculate the optimized value of the threshold voltage using MAP algorithm, This is a simple step. Okay. Now what is ML algorithm? Again the same concept. ML means what? You are not in a position to decide what is P of S1 and P of S2. That means you don't know the relation. So simply what the assumption we make here is, we assume both are equally probable. That means P of S1 and P of S2 both are same. Then automatically this term will become 0 or not. Then what will happen? It will be simply V1 plus V2 by 2. So whenever you use ML coding scheme, name itself tells ML means maximum likelihood decoding algorithm. So when you go for ML, when you don't know the probabilities, then only you go for this. Otherwise don't go. And there is no guarantee that the probability of error you get is minimum. There is no such guarantee. Probability of error is minimum only when you use MAP rule algorithm. That means when you have calculated your optimized value of threshold voltage here, then the probability of error which you get in the final calculations will be automatically minimized. 100%, there is no doubt. But this condition is not there with ML. So whenever you use ML, no condition that probability of error is minimized. You may get a value. Sometimes it may be same, because P of S1, P of S2 you know is equal. MAP and ML both are same. But whenever they are not equal, there is no chance. So that is a very, very important point. So ML rule based algorithm will use considering P of S1 and P of S2 are same. So what is the optimized value of the threshold voltage in this case? Here we should not write actually optimized value of the threshold. Simply we write threshold voltage, that's all. Optimum means minimum probability of error. So this will be simply V1 plus V2 by 2. Second term automatically becomes 0. That's all. So this is how you have to understand these points. So that is the only difference between MAP and ML rule. So ML rule is generally used in so many applications. Like suppose you take a very simple example I will give. Like your Gmail is there, inbox. So sometimes you notice inbox, whenever an unknown person sends you a mail, okay, you may get mail from so many advertisements also, no? Like this HDFC banks or some other things. Randomly they will keep on sending. Just if you have a mail ID, that's enough. You observe those mail IDs will not come into your inbox. They will go into trash or some other heading will be there. They will stay there only. You have to intentionally go there and check. That is the reason generally whenever a new mail comes, you will also get a message on your mobile. A mail is sent to you. If it is not in inbox, please check the other area also. So you will go into that locations and check. If that mail is there, what you will do? You will simply tick that and say convert into inbox or shift it into inbox. Once it goes into inbox, if the same person again sends that mail, it will never go into other location. It will come into your inbox only. There we are applying actually this algorithm. ML, what it will do, you don't know the priority of that sender. You cannot tell. So every mail, if it comes and sits in your inbox, your usage on your Gmail becomes very, very high. They cannot maintain that. So they cannot give like 10 GB, 20 GB for inbox only. So what they will do, they will keep a restriction. Only permitted mails will come there. So all this will be treated as trash and will go into another folder. Once you keep condition saying that it should come into my inbox, then ML is converted to MAP. Priority is given by you. So the next time that mail comes, it will go into your inbox. That is the difference. So ML will treat everything equally. There is no priority, but MAP, priority. Keep that point in mind. I am just linking our concepts with a generalized example so that you will have a little bit clarity. Actually, these concepts are more used there in compared with our communications. But this is a very, very important area where we are using these algorithms. Hope these points are clear. So I have taken a derivation of optimum value of threshold voltage for a baseband or a band pass receiver in digital communication systems, provided my noise is Gaussian. If your noise random variable changes, the methodology remains same. Point of intersection you have to calculate carefully. So they may give a triangular density function. Then it is very simple, na? Two line equations intersection. Here, because you have a Gaussian random variable, you have to take that Gaussian density function, equate it. That's the reason we will get this big formula. This you memorize, because sometimes in numericals, direct 2 marks questions they are giving on this. Just a simple substitution, you will get your answer. I am not telling anything like, just a moment, I will just have a small sip of water. These questions are coming directly in your exams. Just see one question. I have kept one question here. See here. This is a gate question only, direct 2 marks bit. So see the data, how they have framed the question. Consider a communication scheme where binary valued signal x satisfies probability of x equal to 1 is 0.75 and x equal to minus 1 is 0.25. Understand the concept carefully. What type of coding is he using? Plus 1 and minus 1 means, is it a polar coding scheme? In polar coding only, we will use a positive voltage for bit 1 and a negative voltage for bit 0. That is the first point. Now, what is the next point? Instead of writing x equal to 1, I will write as S1 in our logic, just to confuse you. He will give like that. You convert into your formats. So what is P of S1? 0.75 means 3 by 4. So what is P of S2? Automatically it becomes 1 by 4. Okay, E is a combination of your signal, which is x here, either 1 or minus 1, added with noise. Instead of noise given as n, he has used z. Representation change, that's all. Now what is he saying? Z is a Gaussian random variable with 0 mean and variance sigma square. So is our data available or not? So it is taking the form of additive weight, Gaussian noise, whose value of mean is 0 and it is having a variance equal to sigma square. So all our noise characteristics are 100% matching here. Okay. Now what is he saying? The received signal y is fed to a threshold detector. So he is using this word threshold detector. The output of the threshold detector is, it can be either plus 1 or minus 1 depending on the value of threshold voltage which you are setting here. That threshold voltage is nothing but y, tau. So here this tau is nothing but your value of threshold voltage. Now see here, to achieve minimum probability of error, so P should be minimized. The threshold voltage, that means what? Is it optimum value of threshold voltage or not? That is what he is asking. So everything which we have studied is completely in this question. And it's a 2 marks question. What are the options given? See this. It should be strictly positive. It should be 0. It should be strictly negative, or positive, 0, negative, depending on the non-zero value of sigma square. So what is our formula here? The value of this optimum value of threshold voltage in this question represented as tau should be equal to this value of V1 plus V2 by 2 plus variance of the noise coming after getting processed divided by V1 minus V2 into natural logarithm of P of S1 by, that is what we have derived, just observe that carefully. V1 plus V2 by 2, sigma naught square by V1 minus V2, P of S2 by P of S1, right. P of S2 by P of S1. Done? Now just substitute your values. This tau will be equal to, first part will become 0. Correct or not? Polar. plus sigma naught square divided by V1 minus V2 into natural logarithm of 1 by 4 by 3 by 4. Correct or not? P of S2 is 1 by 4. P of S1 is 3 by 4. So you will get a 1 by 3. That's all. Is it clear? Now, this part of data you have here is positive. Power is definitely positive. Denominator positive. V2 is negative of V1. So positive. And this value you are having natural logarithm of a value less than 1 is negative. So you are multiplying a positive value with a negative value. So what should be your tau? It should be definitely less than 0. That's all. Because you cannot calculate the sigma naught square. He has given just a sigma square. That is at the input of receiver. By the time it comes at the input of threshold detector, value will change. And V1, V2 are not 1 and minus 1. Be careful. 1 and minus 1 are actually S1, S2. After they get processed, they will get changed to V1 and V2. That also we cannot find. So only this value will determine it. It is definitely less than 0. So what will be your right answer here? Definitely, whatever the options he has given, it should be strictly negative. Finish. See how you can get that 2 marks very, very, very easily. So just based on that formula. So don't memorize. If you memorize what the problem you will face is, for time being it represents a easier one only. But later on it becomes very, very tough for you. It is not so easy. And I have explained it to you very clearly in 1 hour. Total today class I have taken on this. So it is not so simple for you to use everywhere. Condition is noise should be Gaussian. Then only you can use this. If noise is any other format, the same procedure. So I have covered optimum threshold voltage meaning, how are we getting it using MAP, how are we getting the values if ML is used, and derivation only when noise is Gaussian. Concepts remain same if you go for any other case. So these are the points that you need to understand. So I have taken very effectively all the points. Actually, I want to cover more, but time is not sufficient. Whatever the time that we can cover, that I have put it very clearly here. So many students have problem in these derivations only. Derivations are never asked in exams, especially in gate-like papers. But these type of things you need to know. Otherwise, it is impossible to understand the concept. So that is the reason I have taken it completely. So actually, I want to take 2 topics today. One is this threshold voltage calculation. Another is on constellation plots. But unfortunately, time is not sufficient. I will try to plan one more session, maybe after some days, and I will take that topic also, because that is also a very important topic for GATE examination. Hope you understand this concept. You take the notes, at least practice 2-3 times, and work out with different examples. Already, if you refer previous GATE papers, especially noise-related questions in bandpass, they have given questions when noise is triangular function, when noise is uniform random variable, when noise is a double-sided exponential, along with noise when it is Gaussian. 4 cases are there. I have taken 1 case. Remaining 3 cases also, the concept remains the same. And they are much more easier when compared with this, because here Gaussian curves you need to draw. They are very simple. So use those logics, same concept, do that. Then you will get a better grip on this concept. Is it clear? So whenever you take your VOPT as this region, so what is happening here? Just try to understand. So whenever your received voltage comes somewhere in this region, this is actually our white curve. White curve means S2, but it is coming on a value which is greater than or equal to VOPT. So what is the meaning in this statement? All this will be your error region where you have done transmission of S2, but it is getting transmitted as S1, or I mean received as S1, because it is falling under this yellow region. So this part of our is our error. Now similarly, what is the other error region? you can take this part. This yellow curve actually belongs to S1, but now it is coming less than VOPT. That means what? All this region is probability of error where you have done transmission of S1, but it is decoded as S2. Finish. So this is how you will calculate the error. So what is your total probability of error? P of S1 means first you have done transmission of S1 and the probability that S1 transmitted is decoded as S2, or means plus you have done transmission of S2, S2 transmitted decoded as S1 means S1 given S2. Finish. So this is how you can calculate the total probability of error. So once you have this optimized value of threshold voltage, identify these regions, take the area under that region. So that becomes the total probability of error. So this is a total story in calculating optimized value of threshold voltages, so that this probability of error you are getting here will automatically get minimized. Okay, so hope you understood these concepts. Try to make your own notes on this topic. Very helpful, and definite 2 marks questions are coming in every year of your GATE exam. Okay, hope you got all these points. I'll stop here. If other session is available, we will notify you. I will try to cover one more topic, that is constellation plots. Okay, right. Thank you and all the best.